Today I want to talk about optical device and some memories. Okay. We want to talk about laser and some metrics. First, the metrics is there is two kinds of metrics, passive and active. Passive metrics have is like this. There is four row and um four something link. So if 1000 and here is high and there is ground, and if there is 1000 and then the diode is like this here. So here is 1, so high and 0 in 1, so this diode only operated. But active matrix doesn't operate like this. There is two transistors is in here and capacitor is here. So first one transistor will be operated and data comes here. So if data is 1 and goes here and transistor 2 is on, so VDD like there, so OLED is operated. So row selection if row selection is 1 and data is with 0, OLED does not operate it. Active matrices advantage is low power consumed. Passive matrix have to have a DC bias, but this is not needed. This is the active and passive matrix, and OLED and LCD matrix like this. Because of using OLED, this is the armor pose. When we have to grow on the glass panel. So and silicon LED is the silicon, like a silicone made of silicone. This is the crystalline. So glass is amorphous and silicone is crystalline. So this is not matching. So this is very difficult to grow, take on the glass panel. But OLED is made of polymer. It is made of not poly amorphous. So it can be very easy to grow on the glass panel. But amorphous mobility is so low, so we so this solution is LTPS. It's like a laser onto the glass and amorphous silicon circuit, and like this very fast through the circuit, and it gets a heat and like a little melt and crystalline, so it's become polycrystalline, so mobility is better, but this is a little bit have much sequence and much have operation a little bit not good, so we use in this days we use oxide semiconductor. Light application. Okay, and this is we will talk about laser. Laser is light amplification by stimulated emission of radiation. We yes, last week we I talked about what is stimulated emission. So laser is using stimulate emission. Okay. Um, this is the same stimulation emission when light electron is on the conduction band, and when lights go into the electron, and electrons go down and emission the light. So when it um, lights can be coherented light wave, and it can be amplified. It can be amplified. So this is the lasers operation sequence. First, pump energy, like the go to the balance band to go to the electron balance band to conductor band. So it's pumped into the energy and pumped in energy into the electron. So go up electron and goes down in spontaneous emission, and light emission, and start to stimulate it on other atoms. So it's like a advantage avalanche effect like this. So it's go and both sides is reflection, so can be reflection, so very many reflection in there, so go out to the here, so it's laser. Laser diode is similar to LED, so it's conduction band to valence band and light emission, but it's very heavily doped, so whole Fermi level is up upper the N-type conduction band, and conduction band is upper the Fermi level, so very heavily doped, and this is the spontaneous Laplace frequency domain graph, and when it's laser after the laser operation sequence is very highly, like this here, very high at one point. This is the laser's operation. And similar to LED, there is quantum well in the LED band gap. And CCD is like a matrix, So go when many lights are very lot of lights, and current is very high, but light is small and current is small. So it's like a water in the bucket. So go there, and all of the like here is very difficult, but these days we use CMOS image sensor, CIS, and when this is photodiode, so photodiodes made a current, reverse current, so current is like here, and when initial condition, this junction capacitance have a lot of energy by a VDD, so very many. And when readout is on and turn on and goes here, when this current goes through the diodes, so capacitance energy of capacitance goes down, and when CPU want to select, and this transistor is right on and goes out, okay, goes out. And M4 is resistance, like a resistance, so through like along the capacitance energy. Okay. And we can, and I'll talk about memory. There is very many memory type in here, but we will talk about SRAM, DRAM, and flash. Memory architecture is like this. So very many matrix in here, cells in here, and row and column decoder is here. So when we want to read one cell, and row decoder and cross the row and column decoders in one point, that is what we want to read cell. Okay. SRAM is very high speed and high cost, very high cost memory. This is used to cache memory in the CPU. They have 6 transistor in SRAM, one cell. This is an operation like a latch. You know latch. Inverter is 2 inverter in here, and transmission gate, 2 transmission gates. So when we want to write a data, and BL goes here and write and latch the data and go very we can memory the data, and when we want to read the data and goes up. Okay. And DRAM is like a dynamic RAM, so it's dynamic into through the time, because DRAM is made of one transistors and one capacitor. One capacitor is memorize the data and transmission the gate. So goes here, we write the data and memorize the data in the capacitor, but capacitor has a leak current, so when times go and data will be by volatile, but so we need a refreshing. It's come with the power consumption. So why this is because of the why SRAM and DRAM is called volatile memory. Refreshing is because of the power consumption, so we need to lower the power consumption. So we have to get more. We have to we need a longer refreshing time. So it's C is the epsilon a over t. So when area is up and t is down, thickness is down, and epsilon is up, permittivity up, and capacitance is go high. So there is very many solution in here. This is all the area is up like this, and thickness down. So this is the summary of the SRAM and DRAM. Okay. And this is the flash memory. This is like a FET, but there is a floating gate in here, so this is the flash gate, flash memory. So when we want to write a data in the flash, then write bias in here, and channel is on, and electrons are into the goes into floating gate by the tunneling or hot carrier injecting. And when we want to erase the data, goes down to channel. Okay. So this is the operation of the so when VT when write the in data in the floating gate, threshold voltage is changed, so we can separate the data exist. So when data is no data in the floating gate, and this here, and when data in the floating gate and here like this. So when read voltage is here, so voltage is here, data is not here, and when voltage is here, data is in there like this. So we can multiple the data we read, so like this, VT 1 2 3 4, and we read 3 we read. So we can read data to 1 cell and 4 bit and 8 bit like this. So when only 1 byte in 1 cell, we can say single level cell, and 2-bit multi-level cell, and 3-bit and triple level cell. When go more data in 1 cell, then usable lifetime is go down. It's like a trade-off. Okay, thank you.